Okay, so one of the differences we've already talked about between Earth and Mars is the observation made early in the Mariner program that Mars has no global magnetic field. And today we're going to look at that question in a little bit more detail. But first, I want to talk a little bit about, geophysical structure of the Earth. How many of you have seen this kind of a diagram before? Okay, what's being represented here?
The Earth's crust and its core.
Earth's crust and core, and what else? Mantle. And in the case of the Earth, we've got the core differentiated into an inner solid core and an outer molten core. I was going to say liquid, but molten is a better term. The bulk of the volume of the interior of the Earth is the mantle. Core is made up of what kind of elements? What would you expect to sink down to the middle of the Earth during its formation? Metal, all the heavy stuff. Okay, so the core is primarily, iron, nickel, various compounds of metals with sulfur. We don't find lighter minerals like silicates and so forth in the core. Those are, those have risen up to the top in the mantle and in the crust. How many scientists have been to the core of the Earth? Zero. Okay. How many scientists have been to the mantle of the Earth? Zero. How many scientists have sent any instruments to the mantle of the Earth? Zero. Okay. We have visited the moon more than we have visited the interior of the planet. Okay. Why might you expect that visiting the mantle would be difficult? Okay, we assume temperatures are going to heat up the further down in the Earth you go. We see that certainly in deep mines, the deeper the mines. You've got some pretty deep mines in South Africa going after some various minerals and diamonds and gold and so forth. And some of the biggest problems they have is how to keep those mines cool enough for people and machinery to actually work. And the further down you go, the hotter it gets. And by the time you get to the outer core, of course, you're talking about molten metal, so that's pretty warm. So you've all seen this diagram. Anyone not seen some kind of version of this diagram? Okay. You've seen this diagram. You've taken it on faith. How do we know what we know about the interior of the Earth if no one's ever been there?
The seismic waves.
Okay, seismic waves. Is that what you were going to say, Emily?
I was just about to say, so these are assumptions.
These are our interpretations of what the interior of the Earth would be if we actually took a big knife and cut a section out of the Earth, layer cake-like. This is what we would expect to see. But, we can't just do just-so stories in science. We have to base these conclusions on different kinds of evidence. So seismic waves are one. We've got measurements of heat flow. If this is true, if the interior of the Earth is hot, and we would then expect some kind of heat transfer process that would move that heat from the interior of the planet to the surface where it could be radiated off into space. Various mathematical, geophysical models and so forth.
How far down is the crust?
How far down is the crust?
Or when we get to that?
On the Earth, the crust is... Oh, I should have looked this up before. I'm going to say about 30 kilometers. Okay. Maybe in that 25 to 30 kilometer range. We'll actually see that the crust is thicker on Mars than on the Earth. Okay, cool fun fact there. Or I think it's a cool fun fact, so you have to think it's a cool fun fact. Okay, so
The crust is 6,371 kilometers. Oh, no, that's the distance. Never mind.
Yeah.
Hold on. It ranges from 5 to 70.
5 to 70 kilometers. Okay, yeah. So on average, I mean, the thinner crust would be under the oceans, in particular, some of the ocean trenches. The thicker crust would be in the continental area. Okay. So, one of the ways we can probe the inside of the Earth is through the use of seismic waves, as was mentioned. Basically, we can do an ultrasound of the Earth. Okay, we have earthquakes generating reverberations of the interior of the Earth. The Earth kind of rings like a bell in certain frequencies. And so when you have an earthquake, the energy that's released in that earthquake spreads out from the epicenter where the earthquake takes place, where that break occurs and releases the energy that's been pent up. That energy can propagate out in a couple of different ways. One are these P waves, which are just compression waves. Basically, all of the materials inside the Earth are bumping against their neighbor and pushing them, and that's pushing radiating force out. So that process is very fast. The material doesn't really have to move. It just is kind of this pulse of energy that spreads out through the material that's on the inside of the Earth, through this compression and what's called rarefaction. This squeezing together and spreading out of the material as the wave of energy flows through. That process, this P wave, is a very fast process. The energy that's released can also cause the ground and the interior of the Earth to move up and down as more of a sinusoidal wave passes through. That takes longer to propagate, so those S waves tend to be slower. So if you look at the seismograph readings of an earthquake, you'll notice that, for example, here we're talking about, an earthquake happening in one location and being monitored in another location. The time it takes those waves to get from where the earthquake was to where the seismic station is going to be a function of the distance, how far away the quake was, and how fast those waves are moving through the Earth. And what we see is the P wave energy arrives very quickly, or relatively quickly, and then that's followed later by this slower, more sinusoidal S wave transfer of energy. So people noticed early on that, if you have the earthquake here, looks like at the North Pole, which is not a high earthquake area. But anyway, if you've got the earthquake here, obviously at these nearby seismic stations, you'll see the P wave arrive and then the S wave arrive, and then the further and further away you get, the longer it will take that P wave and S wave to arrive. But if you get far enough around the globe, you get to a point where no seismic waves are recorded. Now, if the Earth was just some uniform material inside, you would expect just a gradual increase of the length of time it takes the P waves to get there until you got to the other side. And the fact that there are some regions where you don't see any waves showing up, and other regions where it's only the P wave and not the S wave that shows up, was a strong indication that there are different kinds of materials at different layers inside the Earth. And we have earthquakes going on all the time. By measuring whether or not an S wave shows up, the time it takes for a P wave and an S wave to show up in the areas where both are showing up, the time it takes for P waves to show up in the areas where only P waves show up, then that has allowed geophysicists to say, well, in the middle of this ball that we call the Earth, there is some material that's different than what's going on in the mantle that is affecting how the earthquakes are being transmitted. And that is allowed, so if you go to Wikipedia and you say, what's the diameter of the Earth's core, what's the boundary between the inner core and the outer core, all of those levels are basically inferred from these kinds of data. And again, I think the easiest way for you to think about it is just kind of like taking an ultrasound of the Earth, and you can detect that there's this different kind of material in the middle there that we call the core. And then in terms of heat flow, we know that there are different processes of convection and conduction that will move heat from the inside of the planet to the outside. And measuring those heat flows help to factor into the different kinds of models that geologists develop to describe what's going on inside the Earth. What you see on this side over here, this is what one of these heat probes actually looks like. This was basically a bunch of heat sensors being put down into a borehole in a glacial layer in Antarctica. So you've got areas in Antarctica where the ice is kilometers thick. You can bore a hole down and drop down the basically thermometers to measure how heat is flowing through the ice. Do the same thing with boreholes that are bored down into the crust as well. The deepest borehole that we have done, and this is as far into the planet as we get, is this Kola super deep borehole, which is a little bit over 12 kilometers down that they've drilled. Basically just a well hole that has been drilled down that deep. And in this location, that is still in the crust. So we have never directly sampled or measured or done anything with mantle, let alone core material. Now, you might want to do a Google search on well to hell, because if you actually do a search on this Kola super deep borehole, you'll get internet sites that talk about how they have recorded demonic sounds from the bottom of this borehole, and it's kind of amusing. So, all of what we know about what's going on in the Earth and what we have modeled for other terrestrial bodies supports the idea that, kind of as Lowell had talked about, as these primordial bodies begin amassing material through this process of accretion, as things keep coming and slamming in under the force of gravity, that body is eventually going to heat up. The more that you have material coming in, the more it's going to heat up. So, the Earth is going to have heated up more in its past than Mars, because Earth is a larger planet. And you heat up this material enough, and it's going to melt. And when things melt, then they can differentiate. So this differentiation is essentially a very physical process. You've got all this molten material. Some of it is heavy like iron, and some of it is light like silicates. What's the iron going to do when the body is molten? Not a difficult question. The heavy stuff is going to do what? When it's going to sink. Okay, so that's why we expect if this terrestrial body is large enough to have undergone differentiation, is large enough to have heated up, either because of that accretion or also because of radioactive decay. You can't forget that. As long as the body gets molten, then the heavy stuff is going to sink, lighter stuff is going to stay at the top, and you're going to get a differentiated terrestrial planet. Okay. But what about Mars? What would you expect to be the situation for Mars, not knowing anything about the geophysics of Mars?
I mean, since it's a smaller planet, it's a colder planet, it probably has a thinner crust. Well, actually, no, it doesn't.
I already told you I had a thicker crust, so yeah.
But you could imagine that it's definitely not as heated up as the Earth is, and it's a lot.
Okay.
Definitely a lot different.
So what would be the important questions we would want to know about the geophysics of Mars compared to the Earth? We know the Earth is this differentiated system with a inner and outer core, a mantle, and a crust. What's the most simple question you could ask about Mars? Is it the same? Was Mars big enough to have undergone that differentiation process? I mean, if you look, the moon is a little bit smaller. So, we have the same question about the moon. Did the moon get hot enough to differentiate? If we go out, to Vesta or Ceres or some of the dwarf planets, they're even smaller, and other asteroids are even smaller. At what point is it too small to have differentiated? And is Mars big enough, or where does it fit on this spectrum? We know for certain that Mars has differentiated into a crust, mantle, core kind of situation. We know that for a variety of reasons. Your reading talked about using the moment of inertia, how the planet spins on its axis and how it resists change to that axis spin. If you take just a solid sphere of material that is uniform, it's going to have a certain moment of inertia. This is just a classical physics concept. But if you take that same size sphere and have dense material in the middle and lighter material on the outside, it's going to basically spin differently. And we won't go into the mathematics or the details of that, but just by watching how Mars spins, they could tell that it's not spinning the way you would expect if it was just uniform rock from top to bottom. So there's something denser in the middle, and there's something lighter on the outside, and that affects how Mars spins around, and that was known for a long time. Also, we have some meteorites from Mars. These so-called SNCC meteorites, SNC, for these three locations where we first found large numbers of Mars meteorites. And by looking at the elements that are in there, we can tell that they're relatively, they have lower amounts of iron and other heavy elements that we would expect if Mars had not differentiated. If most of the iron of Mars sinks down to the bottom, that's going to leave the crust relatively reduced in iron compared to an undifferentiated body like a smaller asteroid. And so by looking at the elemental composition of the meteorite samples that we do have, we can tell that this looks like crust material that's lost some of its iron. And where would Mars have lost its iron to? It would have lost it to the core. Okay. So, I want you to focus on, we're making these claims about the Earth first of all, and then we're making claims about Mars. But to make those claims, we have to have specific evidence that we're basing those claims off of. Okay. So this just summarizes what we know about the inner terrestrial planets, how they differ. So if we take the Earth here as kind of our yardstick that we're familiar with. We know we've got an inner core and an outer core and a mantle on the Earth. Venus is just a little bit smaller than the Earth, and from a geophysics standpoint, it's fairly similar. Got a fairly wide mantle. Again, we have evidence for an inner and outer core on Venus, and the modeling would also suggest this. So, in many respects, in terms of the actual planet itself, Venus is kind of our twin sister, although surface conditions are pretty crappy, as we've talked about. Why don't you see the depiction of the crust on the Earth and Venus diagram? Sloppy illustrator?
It's not known.
No, we know how deep the crust is on average on the Earth, and we can infer a crustal depth on Venus as well. The thing is that if you drew the crust here on this Earth, it would be just this very, very tiny thin layer that would almost be undetectable. Okay, so we have drilled down 12 kilometers into the crust. We haven't even made it through the crust. And that distance is so insignificant based on the radius of the Earth itself that it doesn't even show up on these diagrams. Mercury, smaller planet. Mercury is quite a bit different in that it is a much, much, much denser planet than any of the other terrestrial planets. Because of where Mercury forms so close to the sun, a lot of the light material just got burned away and blown off by the solar wind. And so Mercury's not quite a big iron ball floating around the sun, but it is mostly, dense core material. We've been to the moon. We've set up seismic stations on the moon. We know the moon is as well differentiated. There's a little bit of an outer core and mantle. And what we know about Mars suggests certainly a mantle and core. But what we really don't know in detail is the extent to which the core on Mars might be differentiated. One of the big questions is the core on Mars completely solid? Or is there an inner solid core and an outer molten core like on the Earth? This is important because, and this is previewing the bulk of the main point of this little session here. If the Earth's core were completely solid, we would have no global magnetic field. Okay. So a big question is, what's the situation on Mars? Is it a completely solid core, or is it a solid molten core like the Earth? Okay. So just a little bit about Mars's crust. As I mentioned, it is on average thicker than the crust on the Earth. So we actually have a thicker layer of the lightest material surrounding the surface of Mars, and the crust is actually going to be thickest in the southern highlands, where you've got those what would correspond to really continental crust on the Earth. You can kind of think about the northern lowlands to be kind of similar to oceanic crust. It's going to be thinner, and these diagrams here just show some of those vertical profiles. So you can see that on average, the crust on Mars is going to be, again, it ranges, but on average, it's going to be maybe about 40 kilometers in depth. Okay. So the video I played as we were coming in today is all about this InSight mission. InSight is a discovery class mission focusing on the geophysics of terrestrial planets. Really to get a sophisticated geology station on the surface of another planet. Now they could have sent this to Venus, they could have sent it to Mercury, but plan is to send it to Mars to build on the other research that we're being doing on Mars. But basically, you can see the science questions. They really want to nail down the size, composition, and physical state of the core. This key question, is there molten core or not? Really determine the thickness and structure of the Martian crust, the composition of the mantle, how much heat is coming out, what does that tell us about the interior state of Mars, measure seismic activity, and measure the rate of impact of meteorites. So 3 main instruments, basically the seismograph to measure earthquakes and impacts and other similar seismic activity. This HP cubed instrument is basically, rather than drilling a borehole and dropping down a thermometer like we would be able to do on the Earth, we really don't have the ability to send fancy drilling rigs to Mars yet. So the idea is to take a temperature probe and use kind of a pneumatic drill, a pneumatic hammer kind of approach to drill, to force that temperature probe about 5 meters down, about 15 feet down into the surface of the Mars in the place where InSight lands. That would allow the temperature probe to measure the flux of heat coming from deep below up to the surface.
Yeah, when do you think these InSight missions are going to take place?
Well, we'll talk about that in just about 20 seconds. The last instrument is this RISE instrument that really would allow very fine Doppler measurements to see if how Mars is wobbling. And I don't know, have you ever spun a hard-boiled egg versus a not-boiled egg? You spin the not-boiled egg and it wobbles all around because you've got all that yolky and egg white material inside that's not solid, and you try to spin it and it just wobbles kind of uncontrollably. Whereas if you take a hard-boiled egg, spin it, it'll spin like like a marble or top or something. So yeah, if you're ever in a situation where you can't remember whether this egg is hard-boiled or not, and you want to know before you crack it open, give it a spin. Well, Mars spins around on its axis, and by having this RISE instrument in constant contact, being pinged by the Earth, you get very accurate measurements on to the extent to which Mars is wobbling around on its axis, which would also allow us to tell something about what's going on inside. This mission was to launch in next month, basically, which is when the launch window is coming up. ESA is sending one of their ExoMars missions in March, during this upcoming launch window, and InSight was supposed to go as well. But the seismic instrument, this SEIS instrument, is being delivered by basically by the French Space Agency. And a couple months ago, they found that they were having problems with fine cracks in the weld that was sealing this instrument up, was letting in air. The way this instrument works, it requires a very high vacuum inside. And so they tried to repair it. They thought they had the welds repaired, and they were going to get ready to integrate the instrument on the spacecraft, and found more cracks. So InSight is not launching in next month during the launch window because the spacecraft is fine. The HP cubed instrument is fine, the RISE instrument is fine, the cameras are all fine, but the star of the show, which is this seismic station, is not ready to launch. And they made a decision about a month and a half ago that they really could not guarantee that they would have a good fix on the instrument in time for it to be integrated into the spacecraft for launch next month. When is the next time the launch window opens up? Not next year. How many months between launch windows? A little bit more than 2 years, 26 months. Okay, so takes 26 months for, to go from one opposition to the next opposition. The launch window is a few months before opposition. So this would be essentially, the next launch window would be May 2018. And the big question NASA is dealing with right now is this mission going to launch, or is it not going to ever fly? Spacecraft's already been built. All these other instruments have been built. The French Space Agency is responsible for fixing the instrument, the SEIS instrument. Clearly in 2 years they're going to have plenty of time to fix the instrument. Why might you not fly this mission in May of 2018 if you're NASA?
You don't think that it's worth it? If you think that you could spend the money better elsewhere?
Yeah, most of the money has already been sunk in this project, but Discovery class missions have a finite cost cap. And even sitting for the next 26 months doing nothing costs money, because there are salaries and you've got to make new arrangements for launch vehicles and all that stuff. And right now NASA is, I'm sure the brass are really sweating, can they keep costs down over the next 26 months to allow them to send this pretty much 99% ready mission off in the next launch window. What?
Why don't we just fund NASA more?
Well, that is an interesting political question, and we'll talk about politics ongoing as the semester goes on. Actually, the executive branch just released their upcoming budget proposal for the coming year, and so one of the things we will be looking at is, what is the White House proposing, White House and Office of Management budget proposing for NASA budget. How does that get parceled into things like human space flight versus planetary sciences? So we will take some time to look at the NASA budget, because our class being in the spring semester, it's just perfect timing, because always in February the budget for the proposal for the coming year comes out. Okay. So on to what I really want to focus on today, which is global magnetic fields. Won't go into all of the physics that are involved here, but essentially you can generate magnetic fields when you've got electrons moving. Moving electrons generate a magnetic field. And if we've got molten metal in the core moving around, that molten material is electrically conductive. Those currents of molten material in the core generate a magnetic field, which then feeds back in to generate more electric currents in the core, which generates more of a magnetic field. So we have on the Earth what's known as a magnetic dynamo, where you've got this positive reinforcement back and forth between generating a magnetic field, generates the electrical current, which generates the magnetic field, which generates the electrical current, and that has sustained the global magnetic field on the Earth for the last 4 billion years. And why do we like the fact that we have a global magnetic field? Protects us from radiation from the sun, protects us from galactic cosmic rays. It's a nasty world out in space, and our little magnetic cocoon protects us from a lot of this stuff. Actually, the magnetic field that's generated on the inside of the Earth extends out into space, as you can see here. And so, coming out of the north magnetic pole and looping around back into the south magnetic pole, you have these magnetic field lines that surround the Earth. As the Earth gets blasted by the solar wind, that magnetic field cocoon on the sunlit side of the planet gets compressed by the incoming solar wind, but it kind of buffets the wind, makes it go around the planet, provides us protection, and it kind of streams our magnetic field out behind, trailing, away from the sun. So this is a good thing. Okay, so let's do this. Randomize. Lawrence. What's the main point from the clip?
Mars, well, first of all, Mars is very different than our planet, and it's clearly a dead planet that could have possibly, most likely, had life. But because of the loss of its magnetic field, it's a dead planet, and the direction that Earth eventually will head is the same one.
Okay. Yes. Amar, what would you add? Somber tale. Okay, so let's address that first question. We have evidence that Mars lost its magnetic field. We'll unpack that in a minute. Earth's magnetic field is currently in a period when it is dropping. Should we be doom and gloom at this point? Why not? Okay, so Elaine, what would you add? Why should we not be concerned about our magnetic field in the Earth declining right now?
Actually, I'm not sure, but some people might say like we might have gone to other planets.
Okay, so A, you don't know how fast it's declining, and B, I may be dead before anything is at issue, and C, we might be somewhere else. But what did I tell you about the Earth's magnetic field?
It resets a lot.
It resets a lot, Tim?
Well, no, I was just gonna ask, like, when it resets, do we know how long it stays, like, off, or?
It'll be down for a couple of centuries. We'll have northern lights showing up, all around the globe, and not just at the northern and southern hemisphere. This has happened, as we've talked about multiple times in the past. Have birds gone extinct because of it? No. Okay, so life has been through this process of the Earth's magnetic field collapsing and resetting multiple times, and we're not going to go, we're dying, we're getting scorched by the sun, skin cancer rates go up.
So what will happen to the Earth when that happens?
Well, like I say, what happens is that the magnetic field gets more and more chaotic. You see, basically, you don't just see things disappearing. You see little blebs of north polarity magnetic field in the southern hemisphere, and little areas of. Right now, there's actually a fairly strong anomaly in the South Atlantic Ocean. Okay, instead of just a uniform southward, south magnetic orientation to the magnetic field, there's already, this area. Now, does this mean we're imminently in time, ready for a collapse? I don't know. It'd be very unusual for us to happen to be around at the time when, some geologically significant process takes place like this. But, if it has been like 700,000 years, like I was thinking off the top of my head, we might actually be overdue.
Oh, yeah. What do you think that a reverse in what's the word? You know what I'm trying to say? Like a reverse in our magnetic field. What do you think that would do to the planet?
Planet would not really notice it.
Yeah.
It depends on what you mean by planet. I mean, our traditional magnetic compasses won't work for a while, but we have GPS systems, so will this be a problem for migrating birds that might, you navigate by magnetic field? Maybe. They would have to adapt in some way or another.
If we lost our magnetic field, wouldn't we lose all the satellites that are going around the Earth? Will we lose all of that?
Well, if we were able to just shut off the magnetic field in the Earth, the trajectory of the satellites would not be affected. Okay, they're up in space. They're flying under basically. They're curving around in response to the gravity of the Earth. They would be exposed to higher levels of solar wind, so they would be more exposed to geomagnetic storms coming from the sun. We'd have to be more careful about protecting them, shutting them down when the sun sets off a big coronal mass eruption. But the loss of the magnetic field would not directly influence the activity of the satellites. Okay, so Michael? No. Wait. What does Hellas Basin tell us about the magnetic field on Mars? Tim, help Michael out.
It says that it's been going for a while because when the craters hit, isn't that when he was talking about when they both hit and they weren't magnetized at all?
Right. So I want you to think through the logic here. We have these two big impacts that we can date, and how would we date how old Hellas Basin is? You already know that. What would we do to tell how old Hellas Basin was? What are you doing for the take-home problem for the midterm exam?
Wouldn't you like be surveying the layers of the rocks?
No. How do we date surfaces on Mars? By counting the craters. Okay, so how many big craters, how many small craters? Hellas Basin itself has lots of craters in it, indicating that it is an old feature. And if you did that plot of what's the density of craters versus size of craters, it would be out on that 4 billion year old line. Okay? So we know Hellas happened a long time ago. We also expected it would have happened a long time ago because it was earlier in the solar system that we had those big pieces of rock flying around to slam into planets like Mars. Now, Hellas Basin impact occurs. The crust gets molten. If Mars still had a magnetic field, what would happen to Hellas Basin when that crust solidified?
It would be magnetic.
It would be magnetized by the magnetic field. The fact that the crust that became Hellas Basin did not pick up a magnetic signature means what about the global magnetic field of Mars at that point?
It was
Already
already gone.
gone. Okay. So the fact that we see magnetized crust tells us at some point in the past Mars had a magnetic field, but by 4 billion years ago it was already gone. When was the earliest it could have arisen? How old is Mars? How old is the solar system? This is something you should have off the top of your head at this point. John.
The solar system is
6 billion?
No, less than that. Down a bit. More than 4. Because Hellas Basin occurred at 4. Less than 5. 4.6. 4.5. Okay. So the earliest Mars could have had a magnetic field is somewhat younger than 4.6 billion years ago, because the Earth, the crust would have had, I mean, the planet would have had to differentiate. The core would have had to get cranked up. You know, it may have probably taken 100 million years or so to get the magnetic field going. So Mars had a global magnetic field, but only for maybe about 500 million years. And we can tell that, even though none of us were around 4 billion years ago, by looking at the rocks, by counting craters, and by measuring remnant magnetic fields in the crust today. And so that, that kind of process of putting the evidence together is what, makes, I hope you see science as a very creative process and not just this dull accumulation of facts about the world. So we've had a magnetic field for, well over 4 billion years. It's served us well over the time that we've been here on the planet. Mars could have only had a magnetic field for 500 million years at most, early in its history. Okay. So I don't want to use up all of our time. I do want to start a little bit on the Mars other thing. But, I mean, this is what it looks like. These batches of red and blue color represent areas of different magnetic polarities embedded in the crust, imprinted on the crust. Okay. This is magnetism that is being detected currently by Mars Global Surveyor is not around anymore because it suffered an unfortunate accident. But this was current magnetic field measured by Mars Global Surveyor. Where on the planet is that magnetic field coming from?
Southern hemisphere.
What?
Southern.
It's southern hemisphere, but which layer of the planet's interior is that magnetic field coming from? Is this coming from the core? No. Core is dead. So this is remnant magnetism imprinted on the crust, the rocks in the crust, and strong enough that it can be detected from orbit. So Mars must have had a very strong magnetic field back when it did, but then the core shut down for one reason or another. Magnetic field was lost, and we just have this. And it is in the southern hemisphere, which is, why would we expect it in the southern hemisphere and not the northern hemisphere? What do we know about the different ages of those two hemispheres?
The southern is older.
Southern is older. Okay. Northern hemisphere is too young to have been imprinted by the Mars global magnetic field because by 4 billion years ago it was gone. What we do have are little, instead of use the laser pointer, instead of a global magnetic field circling Mars like we have on the Earth, what we have are little tiny areas that have kind of a magnetic umbrella over them based on the magnetism that is present in the crust. Anyone not seen some kind of version of this diagram? Okay. You've seen this diagram. You've taken it on faith. I mean, how do we know what we know about the interior of the Earth if no one's ever been there?
The seismic waves.
Okay, seismic waves. Is that what you were going to say, Emily?
I was just about to say, so these are assumptions.
These are our interpretations of what the interior of the Earth would be if we actually took a big knife and cut a section out of the Earth, layer cake-like. This is what we would expect to see. But, we can't just do just-so stories in science. We have to base these conclusions on different kinds of evidence. So seismic waves are one. We've got 0. How many scientists have sent any instruments to the mantle of the Earth? 0. Okay. We have visited the moon more than we have visited the interior of the planet. Okay. Why might you expect that visiting the mantle would be difficult?
Too hot.
Okay, we assume temperatures are going to heat up the further down in the earth you go. We see that certainly in deep mines, the deeper the mines. I mean, you've got some pretty deep mines in South Africa going after some various minerals and diamonds and gold and so forth. And some of the biggest problems they have is how to keep those mines cool enough for people and machinery to actually work. And the further down you go, the hotter it gets. And by the time you get to the outer core, of course, you're talking about molten metal, so that's pretty warm. So you've all seen this diagram. Okay, so one of the differences we've already talked about between Earth and Mars is the observation made early in the Mariner program that Mars has no global magnetic field. And today we're going to look at that question in a little bit more detail. But first, I want to talk a little bit about geophysical structure of the Earth. How many of you have seen this kind of a diagram before? Okay, what's being represented here?
The Earth's crust at its core.
Earth's crust and core, and what else? Mantle. And in the case of the Earth, we've got the core differentiated into an inner solid core and an outer molten core. I was going to say liquid, but molten is a better term. I mean, the bulk of the volume of the interior of the Earth, measurements of heat flow. If this is true, if the interior of the Earth is hot, and we would then expect some kind of heat transfer process that would move that heat from the interior of the planet to the surface where it could be radiated off into space. Various mathematical, geophysical models and so forth.
How far down is the crust?
How far down is the crust?
Or when we get to that?
On the Earth, the crust is, I should look this up before. I'm going to say about 30 kilometers. Okay. Maybe in that 25 to 30 kilometer range. We'll actually see that the crust is thicker on Mars than on the Earth. Okay, cool fun fact there. Or I think it's a cool fun fact, so you have to think it's a cool fun fact. Okay, so
The crust is 6,371 kilometers. Oh, no, that's the distance. Never mind.
yeah,
Hold on.
this is the mantle. Core is made up of what kind of elements? What would you expect to sink down to the middle of the Earth during its formation? Metal, all the heavy stuff. Okay, so the core is primarily, iron, nickel, various compounds of metals with sulfur. We don't find lighter minerals like silicates and so forth in the core. Those have risen up to the top in the mantle and in the crust. How many scientists have been to the core of the Earth? Zero. Okay. How many scientists have been to the mantle of the Earth?